The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Very simple little demonstration, and I would like you to take a look at the two materials that are in the two vials I have here. One of these that I'm tapping is a beige colored solid, and it is iron dichloride, ferrous chloride. And then over here I have an organic molecule that's colorless, just white. And what I'm going to do is first make a solution of the ferrous chloride in water. Just using a very small amount. And what you'll see is that the FeCl2 dissolves up pretty nicely in water, and it gives a solution that has very little color to it. You might be able to see that it looks maybe pale yellow. You see that? Okay, so now to that solution of ferrous chloride in water, I'm now going to add this organic molecule. I'll draw the molecule for you before we finish today. I'm just going to add a small amount of this colorless organic molecule. Okay? To get a very nice, intense red color in the aqueous solution. Okay? And the person I'm going to be talking about today is the one who really figured out what's going on in a reaction like that. Okay? And this was a great mystery for a long period of time until Alfred Verner came along. I would encourage you, while you're at home perhaps or visiting friends over this coming weekend, to go onto the internet and go to the Nobel Prize website, where you can read a very nice short biography of Alfred Verner, because he won the Nobel Prize in 1913. And he won this prize based on a theory that he developed stemming from observations he made regarding reactions of metal salts with various substances. And I'm going to point out initially here that he studied the reaction of cobalt-3 chloride. So I just used iron dichloride. This is cobalt trichloride reacting with 6 equivalents of ammonia, and observed that if to an aqueous solution of cobalt trichloride was added 6 equivalents of NH3 ammonia, followed by silver nitrate, that resulted in no AgCl precipitate. And that's rather astounding because, we will get to know, but this one is all. Okay, how does he do this experiment? He just puts these things in solution, adds silver nitrate, and either there is or is not a precipitate of silver chloride, which is very insoluble, and that precipitate can be collected by filtration, dried, and then weighed. And then in comparison with the mass of the added substances, you would know how much of the chloride that was put into the reaction actually came out as insoluble silver chloride precipitate. And he did a series of experiments. And so if he uses cobalt trichloride and less ammonia, namely 5 equivalents of ammonia, then he finds that leads instead to 2/3 of the possible AgCl precipitate. And continuing down, if he uses now only 4 equivalents of ammonia, then the addition of silver nitrate provides 1/3 of the total precipitated chloride. And then finally, if he drops down the number of equivalents of ammonia to 3, then we get none, 0 of the AgCl precipitating. And a further observation to add to these 4 observations was that in no case here did the solution give a reaction with hydrogen chloride. What's the significance of that? Hydrogen chloride, of course, is a strong Bronsted acid. And if you have a base in solution, it should react with that Bronsted acid, right? Okay? And what are we adding here? We're adding ammonia. And ammonia is a base, isn't it? Okay? But when you do the experiment like this and then test for any reactivity with hydrogen chloride, there's no reactivity with hydrogen chloride. So what's going on? And secondly, normally this reaction with silver nitrate is used to quantitatively precipitate chloride from solution. So it's a quantitative analytical test for chloride in solution. And the more, the less ammonia we add, the less silver chloride we're getting as a precipitate. How are these facts related? Well, Alfred Verner put it all together, and he correctly formulated these complexes. Let me write this as follows. In that first instance, when we've added 6 ammonias, Verner decided that the reason that ammonia is not in solution in a form that's reactive with hydrogen chloride because the ammonia is coordinated to the metal. And so he wrote the formula this way: cobalt and H3 6 times. And this species is a trication. And to balance those 3 positive charges, we find that there must be 3 chloride ions outside of what we're going to call the inner coordination sphere of the cobalt complex. Now, there were lots of different preparations that had been reported in the literature back at this time of materials that seem to be composed of metal ions and mixtures of chloride or ammonia or other types of molecules. And this kind of a formulation of them was completely unique. And I really think that in the history of chemistry, you can compare Alfred Verner's leap, his development of the coordination theory, as very much analogous to Kekulé's description of planar benzene with all equivalent CC bond distances. This is a really tremendous leap in our thinking about molecules. And then in the case where he's adding 5 equivalents of ammonia, those 5 equivalents all go onto the cobalt, and so does 1 chloride ion. So he writes it that way. And that chloride ion is balancing one of the 3 positive charges on the cobalt plus 3 ion. So this overall now has a 2 plus charge, and there are 2 chlorides external to balance the charge on that. And then in case 3, we've added 4 NH3 per cobalt to solution. 4 of them go on the metal, and 2 chlorides remain and interact with the metal in a way that we'll discuss shortly. And that system now has 2 of the +3 charges on cobalt-3 balanced by chlorides that are in the inner coordination sphere, and only a single chloride now is needed externally to balance that charge to give overall a neutral system. And then finally, when only 3 equivalents of ammonia are added to solution, those 3 equivalents per cobalt bind to the metal, and all 3 of the original chlorides can be included in the primary coordination sphere, balancing the 3 positive charges on the cobalt-3 ion and giving overall a neutral coordination complex. So this is coordination theory. And the dominance of organic chemistry at that point in time was very great. So most of the people who were thinking about these unusual substances were thinking that they might have structures analogous to those that organic molecules have. And typical hydrocarbon molecules like N-pentane or N-hexane have sequential joined CH2 groups, repeating CH2 groups in a line. And so the type of formula that you were seeing people write for these molecules at that point in time was, for example, a cobalt, and then NH3, 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 somehow all stuck together in a way that does not seem very intuitive to us today, because we know so much more now, partly due to the accomplishments of Alfred Verner. So this systematic set of observations, the use of silver chloride's insolubility as a means of precipitating it out so that you could distinguish between external chloride from chloride that's actually in the coordination complex. And let me define coordination complex. The coordination complex is a metal ion, plus its ligands. So there's another word that you need to learn in this context. Here, I would like to define the term ligand as an atom or a molecule or an ion that can bind directly to a metal like cobalt in its primary coordination sphere. Okay? And that means that they are directly connected to the metal. And the amazing thing here, and what was so different from organic chemistry at this time, was the idea that a single metal ion can have a fairly large number of ligands. In this particular case, Verner analyzed his experiments with the assumption of coordination number being equal to 6. So here it's 6, but coordination number is a variable that depends on the metal itself, and it depends on the specific choice of the ligands. So some molecules are known in which there are very low coordination numbers. Coordination number can be as small as 2 or 1 in some very special instances for insoluble molecules. And for very large metal ions, sometimes the coordination number can be as great as about 12. So 12 atoms or ions or molecules directly connected to a central metal atom. And ligands don't have to be as simple as chloride or ammonia. Ligands can have some pretty interesting architectures. And you can even dream up new ligands with which to decorate a metal ion and with which to imbue it with special properties for purposes like catalysis. Okay? We'll be talking soon about metalloenzymes. These are proteins as ligands to metal complexes. Okay? And very many important enzymes are metalloenzymes that have these elements from the 3D part of the periodic table bonded. So here's what we call the D block, or transition elements. And in the case of the 3D series, you'll know that we have metals like titanium, vanadium, chromium, manganese, iron, cobalt, nickel. Okay? These are called transition elements because oftentimes in ions stemming from these elements, as you go from left to right across the periodic table, you're adding more electrons to an incompletely filled D shell. And at the end today, we're going to talk a little bit about the bonding properties of transition elements. And that will harken back to what I said with my discussion of carbon monoxide and why it's a poison. And it's the interaction actually with certain d orbitals on the iron in hemoglobin that makes CO a toxic substance. And so how does this work? How do ligands coordinate two metals? Well, one simple way is if you have a ligand like ammonia that is a base, it can also be a nucleophile, and the metal can be the corresponding electrophile. I can draw that as a lone pair, to represent a lone pair of electrons on the nitrogen. Now that we've studied molecular orbital theory, you'll know that I can also call this the highest occupied molecular orbital of the NH3 molecule, and it's the one responsible for the basicity of the ammonia molecule and the one responsible for its ability to serve as a ligand in coordination complexes like these. And you might also suspect that we might have some contributions to this highest occupied molecular orbital from hydrogen 1s linear combinations. So I'll just draw that in to make it a little bit more accurate. And so that you can think of this as a big fat lone pair that will coordinate to Lewis acids. And the metal ion is a Lewis acid. But it's a very interesting Lewis acid because unlike the BH3 molecule that has a single empty orbital, this metal seems to be able to act as a Lewis acid 6 times and coordinate 6 bases to it in forming this coordination complex. And if we go ahead and crystallize molecules of this sort and use X-ray diffraction studies to determine the bond angles and bond distances in systems like this, what we find is that these nitrogens are located at the vertices of a nice regular octahedron. So in the case of our first one, we can draw it out this way. This first one is what would result if to that aqueous solution of cobalt trichloride we were to add 6 equivalents of ammonia. So this is Verner's first system. It is a molecule oriented like this. That lone pair that comes from the highest occupied molecular orbital of ammonia is directed right at the metal from each of the 6 ammonia ligands. And this system does have a 3+ charge that is balanced by 3 chloride ions in solution. Okay, so this locating of 6 nitrogens in an array in space that approximates a regular octahedron is what makes the octahedron such a central aspect of the theory of transition element chemistry. Okay, and if you're going to design molecules that do include these transition metal ions, whether you're going to do it for their color, like the red color there of the iron complex that we made a few moments ago, or whether you're going to do it to take advantage of the properties associated with unpaired electrons, like magnetism, for example. You would begin any such approach with the octahedron as your starting point. Okay. Now, let's go ahead and consider some of the other examples provided to us by Alfred Verner. If instead of 6, we're adding only 5 NH3 molecules for every cobalt, then what happens is we indeed do get an octahedron, but one of the chlorides is not ionized. It's bound directly to the metal, and it is serving as a ligand. And this species, therefore, has a 2+ charge. The cobalt ion is still considered here to be in the +3 oxidation state, and this system is balanced by 2 chloride ions that are floating around externally in solution and that are not in the primary coordination sphere. So these atoms here that are part of ammonia molecules that are bonded directly to the metal are in the inner coordination sphere. That's the inner or primary coordination sphere. What do you think happens if you take a metal salt and dissolve it in water? Okay, I did that a moment ago with ferrous chloride. I dissolved it in water. Water is a very polar solvent. It promotes the formation of ions in solution because of its great polarity. It is good at solvating ions. Water is as a medium. Okay, so if I take FeCl2 and add it to water, as I did a moment ago, and it ionizes, what's happening to the iron? The iron is going to take up water molecules into its inner coordination sphere. So when you dissolve FeCl2 in solution, which might often be written quite simply as FeCl2 aqueous, what you really have in solution is a system in which 6 water molecules are bonded to that iron. And because I used FeCl2, this system had a 2+ charge balanced by the chloride ions, 2 of them that dissociate from the iron and ionize and go out into solution to be solvated separately from the cation by water. Okay? So that initial weakly colored solution contained iron in this form, hexaquo iron 2. And I'll tell you a little bit about what made the color change in a moment. First, I'd like to discuss an issue that arises in the Verner system. And this is the problem of isomerism. Verner found that you could make different cobalt complexes that would have the same chemical formula, but, for example, one would be red and one would be green, or one would be yellow, for example, even though they have the same chemical formula. And that was because, as he correctly reasoned, they were forming isomers. And this comes into play, for example, when you add only 4 equivalents of ammonia to solution. And here's why. if I put the first chloride up on top, as I've done here, there are two choices of where to put the second one that are not the same. I can either put a chloride here, such that we have a bond angle of 90 degrees between the two chlorides, and I'll draw in our remaining ammonia molecules that are coordinated to the cobalt. Okay. This is an isomer that we call cis. That's cis denotes a proximal arrangement of the two chlorides with a 90-degree bond angle between them. And then the alternative here would be to put the other chloride 180 degrees away from the first one, and that gives us what we call the trans isomer. And note that both of these would have a single plus charge. Trans means across. So the two chloride ligands are located in a mutually trans disposition here. Okay. Isomerism is very important. I'll discuss a couple other types of isomerism that you can get and that Verner contributed to our understanding of very greatly. And let me do that by completing consideration of this. You might ask yourself, in the case where we added only 3 ammonias to the solution, is there a possibility for the formation of isomers? And the answer, again, would be yes. We can have 2 possibilities. And this is for our neutral system that contains 3 ammonias and 3 chloride ligands. And let's say I put the first one here, second one here, third one here. That's one of our possible isomers. Of this neutral coordination complex. And then the other possibility, the only other possibility, is with one there, and then the third one here. Okay? And so those are you can try to draw different structures, and you'll see that these are the only 2 possible structures that you can draw for a combination of 3 ammonia ligands and 3 chloride ligands surrounding a central cobalt 3+ ion in an octahedral array. Okay, and these have names too. This one is the so-called FAC isomer. And that FAC is an abbreviation of the word facial, because if you remember that the octahedron is composed of a set of 8 equilateral triangles, then the polyhedron that we call the octahedron has both vertices and faces, and these chlorides in this particular case can be seen to define one of the 8 faces of the octahedron, and so that's the facial isomer. And then the other type of isomer for this type of structure is called MER, and that is an abbreviation of the word meridional, which would be like the meridians of longitude that you see on the globe. So they start at the top and run down through the equator and all the way down to the South Pole. That's your meridional isomer. Okay? These isomers here are called geometric isomers. They're different types of isomerism. Because the complexes that differ only with regard to the spatial arrangement of the ligands, but not with respect to the formula of the system, these would be types of isomers known as geometric. So we have the possibility of cis-trans or FAC-MER geometric isomers for molecules that have the same formula. And then there's a further type of isomerism. And here, again, the contributions of Alfred Verner were exceedingly important. because it was thought that this next type of isomerism was restricted to organic molecules. And this is stereoisomerism. Stereoisomerism is a little more subtle than geometric isomerism. And it is a little more subtle because two molecules that are stereoisomers of each other are related in the same way that your left hand and your right hand are related. They're non-superimposable mirror images. If you can find a way to separate molecules that are chiral, then you can have a sample that can do interesting things, like rotate the plane of polarized light. Okay? This happens when you have chiral molecules. And if a molecule is chiral, that is to say, it's non-superimposable on its mirror image. Okay, and in order to see whether a molecule is or is not superimposable on its mirror image, you really need to get good at visualizing things in 3 dimensions and at rotating molecules around in your mind. Okay? You can also do it on the computer. And doing it on the computer will help you prepare for doing it on the exam where you have to do it in your mind. Okay? But if you like architecture and you like visualizing things in 3 dimensions, you should know that that's a lot of what we do in chemistry. You should think about these molecules, these 3D structures, in ways that allow you to test for a property like stereoisomerism. Now, I mentioned that it was thought that stereoisomerism was a property associated with organic molecules, and organic molecules were compounds of carbon that were thought to be associated with very fundamentally with life and living things. And so the fact that Verner, in one of his most amazing accomplishments, was ultimately able to synthesize a coordination complex that contained no carbon at all, but exhibited stereoisomerism, just shattered that theory and really helped to bring science onto a much more firm footing. And that, that parallelism between organic and inorganic chemistry, I think, has stemmed from this aspect of its history. And so let's look at an example of a molecule that's chiral. That could be made from cobalt. And if you imagine carrying out a reaction like we were talking about up above, but not even giving it enough ammonia to displace all the water molecules, then you could have an intermediate like this. Okay, and in this type of species, what I've got are 2 water molecules, 2 ammonia molecules, 2 chlorides, and so if this is cobalt-3, we would have a single positive charge on that ion. And what I can represent here by a dashed line would be a mirror plane. That's our mirror. And we're going to reflect this molecule through that mirror plane to see what its mirror image would look like. And then if you can rotate it around in your mind, we can determine whether it is or is not superimposable on that mirror image. So I'm generating the mirror image by reflecting this water to this position. This ammonia back here reflects over to here. The top ammonia reflects still into the top position. This water behind the board reflects behind the board. And over here, this chloride coming out in front of the board reflects over to here. And we have one more chloride down on bottom. So that molecule is now our mirror image. And let's see if I can let's go ahead and rotate it like this, okay? Because it's a little hard. I'm going to highlight the position of the two ammonia ligands. And to see if this mirror image is superimposable on the structure we started with, I'm going to rotate this around so that we can put the two ammonia ligands coincident with the two shown here underlined in green on the left. So this is, we're going to do a rotation. And I need to rotate this in order to, I'm going to rotate here around the cobalt-chlorine bond axis. Okay? And I'm actually going to go in the negative direction to generate the following structure. This puts this ammonia up top, and it'll put this one down below. So we have NH3 here and NH3 here. Let me underline them. Okay, so those are in positions coincident, and this rotation also will carry that chloride from the bottom up here into what I may call an equatorial position. And it puts a water molecule down. And that rotation about this cobalt-chlorine bond left the cobalt and chlorine on that bond axis unrotated. And then in the back we have this OH2 molecule. Okay, and what you can see is if you now bring this over, and what we have in fact is a situation where we're not currently superimposable with that choice. Okay, so I generated the mirror image, I've rotated it by 90 degrees around the cobalt-chlorine bond axis to bring these two ammonias coincident with these two. So you can see that whereas we have a water molecule on the bottom here, we have a chloride over here, so that's not superimposable. But we can do one more rotation to check the other possibility, and that rotation will be a rotation by 180 degrees around an axis here that is bisected by, that bisects the nitrogen-cobalt-nitrogen bond angle of 90 degrees, okay? So we'll rotate 180 degrees around that axis, and that will bring our ammonias again into a position so as to be coincident. And rotating around that axis brings a water out front here and puts a chloride in back, rotating around there, and it swaps this chloride with that water molecule. So we now have chloride down and OH2 over here. Okay? And so if we take this, we identify our ammonia positions by green underlining. They're coincident here, and now where we have a chloride coming out, we have a water coming out. So our mirror image is not superimposable on the structure that we generated it from through the process of reflection through that mirror plane. And so what we can say is that this molecule and this one constitute a pair of stereoisomers. And because this condition was satisfied that the mirror image was not superimposable on the structure we generated it from, the molecule is chiral. And you'll see here that I've chosen a molecule that contains no carbon, and yet it's chiral, and it has stereoisomers. And that was thought impossible prior to the time of Verner. Let me show you another example of a molecule that's chiral. And I'm going to use this example also to illustrate another important feature that ligands can have. And that is that they can have more than one atom that can bond to the metal at the same time. I'm drawing a cobalt ion in a 3+ complex that has 6 nitrogens directly bonded to the cobalt. But now, look what I'm going to do. I'm going to put some organic material in here and link these nitrogens by a CH2-CH2 unit, a CH2 chain here. So it's CH2-CH2. These carbons that I'm representing as vertices here each have 2 additional hydrogens that I'm not showing. Okay? And that's typical organic shorthand. And I'm going to suggest that this molecule would be generated by adding 3 of these ligands to the metal center. Okay? And for each nitrogen, if you consider it as being derived from ammonia, one of the hydrogens of the ammonia is replaced with a nitrogen-carbon bond. And so we've used this organic moiety here to tether 2 nitrogens together. This is a very popular and ancient ligand from coordination chemistry. And by drawing in simplistic form the 2 lone pairs on the 2 nitrogens, you can see that this set of 4 atoms is able to organize itself so as to simultaneously point 2 lone pairs at the same metal center. That is permitted by this bridge. This particular ligand is called ethylene diamine. And it is called EN for short, ethylene diamine. And it is an example of a bidentate ligand. And that means that it has 2 teeth with which to bite down on the metal center. It is a double Lewis base, right? And when it binds to the metal center, we call that the process of chelation. When a bidentate or a multidentate, which may be a tridentate or a tetradentate ligand, binds to a metal through multiple points, we call that ligand a chelate, and we call the process one of chelation that forms these ring structures with the metal as part of the ring produced through multi-point binding of the ligand to the metal center. Okay? And you're going to see that it's possible to have all kinds of different architectures for ligands in proteins or in synthetic systems. And the reaction that I carried out over here earlier was one in which I added 3 equivalents of a bidentate ligand to this solution of iron 2+. And when that occurred, this bidentate ligand displaced the water molecules from the inner coordination sphere of the metal, and the bidentate ligand that I used was this one. This is a very common chelating ligand. It is a planar aromatic ligand. And you can see that, like ethylene diamine, its architecture promotes the pointing of a pair of electrons toward the same point in space, so that this ligand can bind itself to a metal center through 2 nitrogen lone pairs simultaneously. And it's the interaction of the d electrons on the iron center with the unsaturated pi system of this organic ligand that produces the red color in ways that we're going to explore in more detail in one of our next lectures. But before we do that, we're going to need to understand something about d orbitals. And as you've learned, when you're forming molecular orbitals in systems that consist of either s or p orbitals, you needed to know something about the nodal properties of those atomic orbitals in order to build proper molecular orbitals. And that will certainly be the case for these more interesting elements that have d orbitals, not just s and p valence orbitals, but also a set of d orbitals. And I call those the 3d elements because their principal quantum number for those elements is 3. And what we need to now know is, what do these orbitals have as far as nodal properties depending on the other quantum numbers. Okay, and I'll draw a set of coordinate axes here on which to map these orbitals. Okay, it should be pretty straightforward for you to keep straight the nodal properties of the d orbitals, of which there is a set of 5. We had one s orbital for a given atom of valence shell, and we had a set of 3 p orbitals, and there is a set of 5 d orbitals for the d block elements. And they can have different values for the quantum number m. One is 0, one is +1, one is +2, and m can be -1, and m can equal -2. Okay? And this quantum number determines the angular nodal properties of the d orbital in question. Okay? Here, let's draw a fairly simple one. Let's say that we have x, y, and z. Okay? Then what we might have is a d orbital that looks like this. D orbitals often have 4 lobes. In fact, you'll see that we represent 4 of the d orbitals this way, and not the 5th. And let me use this pink to represent the negative phase. And so this orbital here is dxz. And that means that it has nodes. You have 2 planes that are nodes for a dxz orbital. And one of these is the xy plane, and then the other one is the yz plane. Okay, so those are planes. When you go from one side through one of those planes to the other side, the wave function changes sign. Okay? And just like a p orbital has a single, each p orbital has a single nodal plane, each d orbital has 2. And this is dxz, and we can also have one that we call dx squared minus y squared, and that one lies right along the coordinate axes like this, with its 4 lobes being skewered by the x-axis and the y-axis, and we have negative phase located along y for the dx squared minus y squared, and you can see that the nodal surfaces here they both contain z. So the nodes contain the z-axis, and they bisect the x and y coordinate axes. So there's one plane up here that contains the z-axis, and one over here located at 90 degrees to the first one. And those are the nodal planes for dx squared minus y squared. I can, in addition to that dxz orbital, I have a dyz orbital, which is located with its lobes lying between the y and z coordinate axes. And it will have phasing as indicated here in pink. Okay, that's dyz, and it looks exactly like dxz, and it's just rotated by 90 degrees around the z-axis relative to dxz. And then finally, we have one that looks just like dx squared minus y squared, and this one is dxy, and it looks exactly like x squared minus y squared. The dxy orbital lies in the xy plane, and its lobes point between the axes, as shown here, that phasing. And then finally, and we'll return to this point next week, our m equals 0 orbital is our dz squared. And dz squared lies along and is skewered by the z-axis. It looks like a p orbital, except the sign is the same on top and on bottom. And then it has this beautiful torus here that is in the xy plane. like that, so that its nodal surfaces are actually conical rather than planes. Okay? That's our set of 5 d orbitals with which we're going to do a lot more to understand the chemistry of coordination complexes. So have a great break, and please don't forget to read about Alfred Verner.